share for letting me speak here. So this talk is about fractionalized charge excitations in a spin liquid on a partially filled particle lattice. So this work is in collaboration with Han-Yang Ki and Yongbei Kim at the University of Toronto. So let me first describe some triangle lattice Hubbard model phase diagram. So this is the expected phase diagram for a triangle lattice Hubbard model at half billion. So when the interaction is the Hubbard interaction is very weak, so we have a Fermi liquid metal. So when the interaction becomes large, we have a mode transition, and the electron becomes localized on the lattice side. So at very large interaction, so we have this 120-degree magnetic ordered state. And in between, in this intermediate coupling regime, so we expect a U1 quantum spin liquid with a spin-on Fermi surface. So this weak model inside quantum spin liquid can be understood from a perturbative treatment. So if you do perturbation in terms of T versus U, versus U, and one can generate many competing exchange interactions, which compete with this nearest neighbor exchange, and which frustrates this 120-degree state, and leading to a quantum spin liquid phase. So this competing interaction includes like four-side spin exchange, long-range exchange. So this has been shown by Mortonich 2005. So this quantum spin liquid and mode transition between a Fermi liquid metal and a U1 quantum spin liquid with spin-on Fermi surface can be described by a slave rotor formalism. So in this formalism, one can write the electron operator as a product of a charged rotor, charged bosonic rotor, and a spin for fermion carries spin 1/2 quantum number. So in the Fermi liquid, so this rotor, this bosonic rotor is condensed, and then the U1 gauge field is Higgs due to the Higgs mechanism. So in the quantum spin liquid mode incident phase, the rotor is gapped, and the low energy effective theory is described by a spin-on Fermi surface coupled to emergent fluctuating internal U1 gauge theory. So you can also see this in the talk by Mendel in the morning. So even though the quantum spin liquid in this triangle lattice Hubbard model has a fractionalized spin excitation, the charge sector of this phase is actually very boring. It's a trivial. It's categorized by a trivial local gapped charge QE excitation. Charge QE is the charge, electric charge of the electron. So the goal of my talk is to provide a possible example of quantum spin liquid whose charge excitation are also fractionalized, not just the spin sector. The charge sector is also fractionalized. And I also want to introduce a slave particle formalism to describe this phase and describe the mode transition from Fermi liquid metal to this mode incident phase. So finally, I will suggest a meaningful physical quantity to measure in a real experiment for this charge fractionalization. So the model is defined. The model is an extended Hubbard model defined on a particle lattice. So this Hubbard model has a Hopin, nearest neighbor Hopin, and the nearest neighbor repulsive interaction, and on-side Hubbard U interaction. So this is the particle lattice. So the electron filling is a quarter in this talk, and a quarter means then the average electron filling is a 2 electron per tetrahedron, 2 electron per tetrahedron. So the Hubbard U, because of this fractional electron filling, the Hubbard U on-side Hubbard U interaction cannot cause in mode localization. So we can set U to be infinity. So the mode localization is really caused by this nearest neighbor repulsive interaction V. So when this V, this interside repulsive interaction is very large, so electron become localized, but the electrons are not localized on a lattice side. They are localized on a tetrahedron cluster. So in a strong V limit, there are exactly two electrons per tetrahedron. So we expect when the Hopin term is dominated, we have Fermi liquid metal, and when this interside interaction term is dominated, we should have this model insulator, but a cluster model insulator, instead of a side mode initiator. So here I first try to describe the mode transition using a slab rotor formalism. In this formalism, as I just described for the triangle lattice, so I write down the electron operator as a product of a charge rotor and fermionic spin-on. So because this description, so the Hilbert space had become enlarged, so I need to introduce this constraint. So this L operator is a conjugate variable of this angular theta. So using this kind of formalism, the Hubbard mode is reformulated into a two-coupled spin-on and rotor Hamiltonian. This is the spin-on Hamiltonian, rotor Hamiltonian. So the spin-on and rotor Hamiltonian are invariant under U1 gauge transformation. So let's look at let's explore this the charge sector Hamiltonian more carefully. Even though the spin-on sector form a spin-on Fermi surface, but the charge sector behave very non-trivially. So this charge sector, so this is the charge sector Hamiltonian. So in the larger U limit, so the favors LZ, this LZ variable, to be either pointing up or pointing down, depends on whether the side is occupied or not occupied. So if we identify this rotor variable as a ladder operator for the spin 1/2 variable, so this charge sector Hamiltonian is nothing but a spin 1/2 XXZ model. In terms of the spin here is just the variable L in the large U limit. So this XXZ model for spin 1/2 XXZ model particle lattice has been studied numerically in a quantum Monte Carlo simulation. So people found when this V interaction is dominated over this hopping term, so we obtain a quantum spin ice phase when this V is very large. So this quantum spin ice is just a U1 quantum spin liquid in a 3+1 dimension. So quantum spin ice in L, in the variable L, is basically a quantum charge ice in the charge sector. So the 2 up, 2 down spin ice rule for the L variable is basically a 2 occupied or 2 empty charge ice rule for the charge sector. So this so we can in a very large V limit, we can obtain the low energy physics from the perturbation theory, perturbative in U J over V. So in third order perturbation theory, we generate a ring hopping around the hexagon that acts on the highly degenerate ice manifold. So this ring hopping is basically just moving this charge from here to here, and moving this charge to here to here, moving this charge to here to here. So it's a third order process. It's a ring hopping term. So this ring hopping Hamiltonian can be mapped into a lattice U1 gauge theory if we identify this rotor variable as a vector potential for the U1 gauge field. So this effective Hamiltonian is become an effective magnetic field term on the dual diagonal lattice, which is formed by the center of the tetrahedrons. So from the properties of a quantum spin ice, we can identify the corresponding property for quantum charge ice in the charge sector. So the low energy physics of the quantum charge ice is identical to the quantum spin ice. So it's described by an emergent compact quantum electrodynamics in a 3+1 dimension. So there is additional U1 gauge structure in the charge sector besides the U1 gauge field, which causing the spin charge separation. So just as the spin quantum number fractionalization in quantum spin ice, so charge excitation in a quantum charge ice is also fractionalized and carrying QE divided by 2 electric charge. It carries half the electron charge. And these are two different fractionalized charge excitation, and they are interacting with the emergent photon degrees of freedom. So to capture this extra charge fractionalization in the charge sector, so we need to modify the slab particle description from this slab rotor formalism to this more complicated slab particle description. So here, the charge rotor excitation is fractionalized into a two charge boson. Here, phi is the charge boson, and each of them carry half the charge quantum number. So this is the cartoon picture of the electron fractionalization in this motor regime. So the electron is a composite of a charge and a charge QE and a spin. So it fractionalizes into a spinon and two charge bosons, each carry half the charge, half the electron charge. So the charge sector in the motor regime become this. So this describes the hopping of the charge boson on a dual diagonal lattice, which minimally coupled to the emergent U1 gauge field in the charge sector. So most transition happens when the charge boson condense. So in a metal phase, the charge boson condense. In this quantum charge ice, quantum spin liquid phase, this boson is gapped. So this is the phase diagram as we tune this T versus U versus V. When this thing is very small, we have more incident phase. When this thing is large, we get a fermi liquid metal. So when the charge boson condense, the internal gauge field in the charge sector is gapped from the Higgs mechanism. The charge fractionalization is destroyed. So the charge boson is also condensed because charge boson is the product of two charge boson. Charge rotor is a product of two charge boson. So when the charge boson condenses, the charge rotor is of course condensed. So when the charge rotor condenses, the spin, the U1 gauge field, which is responsible for the spin and the charge separation, it also picks up a mass from the Higgs mechanism. So the spinon and the charge are then combined back into 4 electrons in the fermi liquid metal phase. So how do we detect this quantum charge ice phase? So to detect the quantum charge ice phase, basically we need to detect the fractionalized charge excitation or emergent gauge field. So here I just describe one method to detect to directly measure the emergent gauge field in the charge sector. So because one can use this inelastic X-ray scattering to directly measure this gauge field correlation in the quantum charge ice phase. So the gauge field, the electric field of the gauge field is basically the density correlation of the electron charge. So this imaginary part of the correlation corresponding to the photon mode in the U1 gauge field. So this is the schematic plot of the emergent gauge photon spectrum at low temperature. So there is an advantage of this kind of measurement because unlike quantum spin ice, for the F electron system, the exchange coupling is very small, so the measurement should be done at very, very low temperature. But for this system, this is the Hubbard model, so the energy scale is much higher than F electron exchange. So the experiment can be done at a very high temperature. So one expect to see much clearer features in the experiment. So at the intermediate temperature, when the temperature is higher than this energy scale, when this charge quantum coherence is destroyed and less than the charge localization energy scale, so in this regime, the system is not in the quantum regime anymore. It's a classical charge ice. So the equal time charge structure factor should show this pinch point structure in the momentum space, just like a magnetic spin structure factor in the quantum spin ice phase. In the classical spin ice phase. So here is some physical system where the model can be relevant. So in these two materials, So both of them have a fractional electron filling on a particle lattice. So for instance, for this material, so this one has a 1.75 electron per site. So the total electron filling is a fractional, is about 1/8. So and this material shows a metal inside transition under pressure. So it can be interesting. It can be very interesting to detect X-ray scattering in this material. So finally, let me summarize this talk. So we propose interesting exotic cluster model inserting phase, in which both the spin and the charge quantum number fractionize. So we develop a slab particle formalism to describe this exotic phase and describe the mode transition to this cluster model inserting phase. So we suggest some physical quantity to measure the internal gauge structure for this charge fractionalization. Yeah, thanks for the attention.
Okay. So questions, comments? I have one question. I mean, these emergent exotic excitations that you're imagining in the charge sector that you would probe with inelastic X-ray scattering. So presumably they would have some interaction with the usual phonons as well, and in fact, you know, depending on precisely what their energies are, they might overlap in energy with optic phonons, acoustic phonons, what have you.
Yeah, that's right. Yeah, so, but the momentum is in a different location in the Brillouin zone.
Oh, sure, yeah. No, I was wondering if they would interact with each other, if the emergent excitation would interact with the phonons.
Yeah, there could be some hybridization, just like a polariton type of physics. Right.
Yeah. Further questions? Yes, please.
I think it could be some instability to structure distortion. I don't know where it will happen. It depends on energy scale. I don't know. I don't know the answer.
Yes, please.
Yeah. Yeah, so that's an interesting question. That's more like if you change your chemical potential, what will happen to the system? I don't know, but I think I can answer the mode transition. So when you double with this chemical potential, if you change your chemical potential, the universal property of the mode transition will change. The dynamical X model will change from. Yeah. Mm-hmm. Sure.
Other questions or comments? Well, if not, thank you very much, gang, for a very nice talk.